Okay, welcome students. Myself, Dr. Omkar Singh. I am the course instructor for this course on signal and systems. I hope you all are fine and doing well, and I pray for your good health in this pandemic and wish you have a healthy and safe stay at your homes. So, we will just introduce the course today, what we are going to cover in this course and why this course is important, especially for electronic students. Okay, this course on signal and systems, I have already shared the textbook with you and the syllabi of this course. So I will just discuss in today's lecture what are the course contents. Okay, so in the very first unit or at the start, we will have an introduction about this course, introduction to this course on signals and systems. Okay, then in the second part we will study linear time invariant systems in a bit more detail. Then third important topic in this course is frequency analysis, right? And then finally we will discuss two major transforms. One is Laplace and another is Z transform. So these are the major topics that we are going to cover in this course. Okay, now say this course on signals and system is very important, and it is basically a prerequisite course for other courses that you will study in higher semesters, mostly for the communication system course and for digital signal processing course. This course acts as a prerequisite course. Whatever concepts you will study in this course, they will be applied in communication and DSP, or maybe another course, wireless communications also. Okay, so without studying the signals and systems, you cannot study the communication systems, you cannot study the course on digital signal processing or wireless communication, or other maybe some advanced courses which may be your elective courses. Okay, so you have to take this course very seriously, and I will try to explain each and every concept in a very transparent way. So in case at any point of time during this course, if you don't understand anything, you can always comment your queries in the Google Classroom. We will discuss all the queries that will be raised by you. Okay, now to start with this course, if you see what is a signal and what is a system. Okay, so we start from signals. What is the definition of a signal and what is the definition of a system? Okay, so signal is basically defined, you can say it is a source of information. Okay, the signal is a source of information, and see in your real life you are surrounded by so many signals. Okay, like my voice, whatever I'm speaking itself, it is a signal, it contains some information. Okay, if you take an image where the pixel intensities they vary with respect to space coordinates, that is again a signal. Okay, you may have a biomedical signal if you go for some test. Okay, maybe if you go for ECG that records your electrical activity of Earth, it is again a signal which contains some important information. If you take your EEG signals, that will record your activity of brains, which we call as brain waves. Okay. So in automobiles, if you suppose you apply some force on the engine and you get a velocity corresponding to that force. So velocity and force, they are also signals. Okay. In electrical systems, basically, or in electronic systems, the signals are nothing but simply the variation of the voltage or current with respect to time. Okay. So every signal, it has some information, and if you look at every signal, it is nothing but variation of some pattern. Okay, this is a signal. So you have some amplitude that is varying with respect to time. Okay, so mathematically we define a signal as a function of one or more independent variables. Okay, so you have function of some independent variable, and mostly this independent variable is t. So we have some variations with respect to time. Okay, so that variation is basically nothing but a signal. So that variation may be a voltage is varying with respect to time, or a current is varying with respect to time. Okay, or any other variable. So this independent variable need not to be always time. It may be other parameter also. Like suppose if you see in geophysics, okay, so the variation with depth of some physical quantity, maybe like with density or with resistivity, that is used to study the structure of Earth. Okay, so in that case, the independent variable is, you can say, another physical parameter. It is not time. Okay, or if you go for the meteorological signal processing, in that case, the variation of the air pressure or temperature or wind speed with altitude, that is important. So altitude in that case becomes independent variable. Okay, and the pressure or the temperature you are recording is as a variations of altitude. So with respect to altitude, your temperature or air pressure is varying, so that is again a signal. Okay, if you say a voice signal or a speech signal, what happens in that, the air pressure, basically acoustic pressure, that is generated by your vocal cords, that varies with respect to time. So we have a pressure which is varying with respect to time in that case for voice. Okay, we have pressure, acoustic pressure, the variations of acoustic pressures with respect to time, that gives you a signal. Anyhow, when you use a mic or a microphone, so these acoustic pressures, variations in the acoustic pressures, they are converted into its equivalent voltages. So if you finally have a voltage as a function of time. Okay, so every signal, it somehow denotes some physical phenomena that is going. Okay, so it captures some information from some system which basically generates the system and generates this signal. Okay, so in electrical systems or in electronic systems, the signals that we are concerned with, we have nothing but a voltage or current as a function of time, the variation in the voltage or current as a function of time, even if the parameter may be some other parameter, but we use sensors or we use some devices to convert that variation into finally a electrical signal. So electrical signal, you have voltage or current with respect to time, a variation that becomes a signal for processing. Okay, like see in the voice or the speech signal, the actual is basically pressure variation with time. Okay, but since you have to process it using electrical or electronic system, the signal must be electrical in nature. And in that case, you use a device, a microphone, which converts the pressure variation into the voltage signal. Okay. The signal can be one dimensional or it can be multi-dimensional. So like these signals, they are one dimensional where the independent variable is t. If you see a image signal, image is basically represented as a matrix. Okay. So you have two coordinates here, this which are called as spatial coordinates x and y, and this image is nothing but an array of pixels. Okay. So each pixel has some intensity or brightness, and that intensity varies with respect to the space coordinates x and y. So you don't have any time information here basically. Okay. It is a position. So the pixel intensity at this point, at this coordinate will be different, the pixel intensity at this point will be different, and so on. So you have an array of pixels where the intensity of each pixel is a function of x and y, the space coordinates. It is called as two-dimensional signals. Okay. Now whatever system or whatever signal processing theories you develop for one dimensional, you can directly apply those on two-dimensional signals. Okay. You have to just made a little bit modification in the algorithms or in the equations. So if you see image processing as a course, so for that you must know fully, or you must understand fully the course on signal and systems as well as the course on digital signal processing. Then it is very easy to understand how the images are processed, because image is nothing but again a signal. Okay. And similarly, if you take a video signal, now in the video signal we have images which are transmitted at a fast, you can say, speed with respect to time. So it is a function of time also. So we have three coordinates, three independent variables. Okay. This is one frame. So you are transmitting multiple frames so that you get a continuous signal which we call as the video signal. So in that case your function becomes your signal, it becomes a function of three variables, space coordinates as well as the time. So at one time you have one pixel intensity, and at the same time when you change the time you will get another pixel intensity. Okay. It means you have one matrix here. At one time this matrix will be different, at next time this matrix, entire matrix will be different, the pixel intensity will change. Okay. This is for a monochromic image. You have only one, or we can say a grayscale image. If you take a color image, you have in that case three channels, RGB. Okay. So in that case you will have three channels, three matrices which will vary with respect to space and time. One is for red color, one is for green, one is for blue. So in that case it becomes a multi-channel and multi-dimensional signal. Okay. So one classification is one dimensional and multi-dimensional. If the signal is function of only one independent variable, it is one dimensional signal. This is what we focus in this course. Okay. If the signal is a function of more than one variables like an image, it becomes a two-dimensional signal. And what is a multi-channel signal? Multi-channel signal means you have acquired a set of signals simultaneously. Okay. Like suppose if you I may take one example, like in the ECG signals, you have 12 lead ECG signal. Okay. This is a standard clinical recording system. Okay. Means at the same time from your human body, you have 12 leads. So you have 12 voltage recordings at the same time. So this is a multi-channel signal. You have 12 channels at the same time. Although it is one, each signal is one dimensional, but you have more than one signals in the same set. It becomes a multi-dimensional signal. Or similarly, if you go for EEG signals recordings, so you have 24 channel is EEG. So your brain waves, they are recording using so many electrodes. Okay. So that becomes a multi-channel signal. right? So you have a signal which has some information in it. Okay, now what is the purpose of the system? The purpose of the system is to process the signal. Okay, so you pass a signal through a system. So you have an input signal here. When you pass it through a system, you get a output signal, which you can say that it is a processed signal. This is what is signal processing. Okay, the purpose of the signal processing or the system is what? To extract some important information from the input signal. Okay, so that processing can be anything. You can design a system for any signal, but before you design a system, you must have a complete knowledge about the signal itself. Okay, so that is why before studying the systems properties, we will discuss about the various types of signals and what are the properties of the signals, so that you can design a corresponding system to process that signal. Okay, so this system which is used to process the signal, this may be a communication system, suppose. Okay, so if you have a communication system, like it may be simply a modulator. Okay, so you have one signal here, and then you have, this is information bearing signal, and then you have a carrier signal here. This is input signal. So you have maybe a modulator here, and this signal will modulate the carrier with the information. You get a modulated signal at the output. Okay, so this is nothing but a system. Now what is processing in this case? In this case, the processing is simply to modulate the carrier signal with the information in the input signal. It may be amplitude modulation, it may be frequency modulation, any modulation. Okay, another example may be, suppose you have an input signal which is ECG signal. Okay, and you have a system which is used to monitor the heart rate. So you have a heart rate monitoring system. Okay, so you apply input ECG signal. The output of this is nothing but to just calculate the heart rate from this signal. Okay, so in that case you have to design a different system. Okay, but before designing the system, you must have knowledge about the input signal that you are going to process. Okay, similarly, if it is an input is an image, you may have an input signal which is an image signal, and the purpose of the system may be to compress this image so that you reduce the size, image compression. So accordingly your system will have different properties. Okay, or if you capture image, the image is blurred, you want to remove the blur from the image, you have a different system for that. Okay, so system is nothing but it is a physical device which is used to process a signal, and by processing the signal we simply means that you try to extract some important information from the signal. Okay, the system may simply be a filter also. So you have some signal which is corrupted with noise, and you pass it through a system. The purpose of the system in that case is just to remove the noise from the signal so that you get a noise free signal at the output. Okay, so we will discuss about some important signals which are very important in the theory of signals and communications. Okay, based on that you can have a well defined mathematical theory, because without a mathematical theory or a background you cannot go for any design. Okay, so in the classification of signals we will concentrate on two important categories of signals. One is your continuous time, and another is your discrete time. Okay, means when you classify signals there are so many classifications, but the basic classification is that either that signal will be in the continuous time or that signal will be in the discrete time. So continuous time signals, they are denoted with x of t, and discrete signals, they are denoted with x of n. In some books they also used this notation. Okay. Now what is the difference between the continuous and discrete time is that when you have a continuous time signal, it means the signal information is present at each and every instant of time. It means time itself is basically a continuous parameter. Okay, you can find the signal value at any instant of time wherever you want. Time is continuous in this case. When you have a discrete signal, in that case x of n, the signal is not present at each and every instant of time. It is present only at discrete intervals. So you may have a signal value at 0, then after some time t you have some other signal value, then after a time maybe 2t another value, and so on, 3t. Okay, this t can be anything. It may be suppose 1 minute. So after every 1 minute you have signal information, in between you have no information. Okay, but in the real life all the signals that we get are practical signals. They are basically continuous time signals. Whether it is a speech signal, whether it is a biomedical signal, whether it is music signal, whatever signal you get in the real life, they are mostly continuous in nature. Okay, these type of signals, discrete signals, they practically you can say in the real world you don't get, but you can have a signal like suppose how you can generate a signal like this. Suppose I measure the blood pressure of my body. Okay, after suppose every 1 hour. So on this axis I have BP, on this axis I have time. So initially at some time I denoted my blood pressure, and it is suppose 120 by 80. Okay, now after 1 hour, this time is now 1 hour, I again record my blood pressure. Okay, so I get a different value. Maybe in this time it is 120 by 78. Then after 2 hours, I again record. It may become 130 by 70, and so on. Okay, so this signal is a discrete time signal. Okay, so you have information about the signal just after every 1 hour. In between there is no information. So discrete signal is nothing but a sequence of numbers, which is called as discrete sequence now. So you may have 1, 2, 4, 5, 7, whatever it is. Okay, it means at 0 instant this was the signal amplitude, then at t, whatever t may be, then 2t, then 3t, 4t, and so on. Okay, now there is one very important thing, that even if the signal is continuous in time, we can process this signal using a discrete time system. Okay, and in that case the important thing is that you have to convert the continuous time signal first into a discrete time system. Because when you see systems, for a continuous time signal you have a continuous time system, you have a xt, you pass it through a continuous time system, you get a output yt, which is again a continuous time. In discrete time systems you have xn, a discrete sequence. Your system is a discrete time system and your output is yn, which is a discrete sequence. Okay, so this continuous time signal, it can be processed either using continuous time system, or there is an alternate way to process this signal using a discrete time system. For that you have to convert this continuous time first into a discrete time, and that is done by sampling, which is very important topic in signal processing or signals. So sampling is a process which is used to convert a continuous into a discrete signal. Okay, and what we do in the sampling, basically we simply sample the continuous signal after an interval of t time. Okay, means now we are not storing the continuous signal information as it is, but we store only the information about the signal at 0, then at t, then 2t, then 3t, 4t, and so on. So what you get at the output xn is nothing but a sequence of numbers. Suppose this value is 2, this may be 2.1, this may be 2.2, 1.9, 2.5, this amplitude. Okay, so you're getting 2, 2.1, 2.2, 1.9, and so on. So it is a sequence of numbers. And now this n in this case is basically not time. Okay, this n just denotes the sample number. It means at this point, this is for n is equal to 0, so the first sample. This is for n is equal to 1, the second sample. Then n is equal to 2, next sample, and so on. Now this n is not time. Even when you have xt, t itself is the time. But when you have xn, you have basically lost now the time information. It means if I just give you this sequence of numbers, and if it is converted from a continuous time signal, okay, so you must have the information about t. Otherwise, if just this sequence is given to you and you don't know about the sampling time, you will not be able to recover this continuous signal back from its samples. So that is very important. Okay, now in the discrete signals, time has no significance. As you can say, time has lost its significance. It is just a sequence of numbers. Okay, so what it means is that if suppose I give you a signal xn is equal to 1, 2.5, 2, 6, and 8, and I say that this signal was basically obtained by sampling a continuous time signal. So there can be so many signals in continuous time from which you can get the same signal, isn't it? So what is time in this case? In this case, n is nothing time, n is not time. Time has lost its significance. So this is the important difference. Suppose I get one signal like this, okay, another signal like this. Maybe these are two different signals. If I take one sample value here, then here, then here, here, and here, okay, 0t, 2t, 3t, 4t, 5t. After I have t samples, the output is same whether you take it from this or whether you take from this. Okay, so how you are going to reconstruct this if the samples are just given to you? So that answer you will get in the sampling theorem, that how you should choose the sampling time. Okay, so the important thing to note in this discrete signals is that this n is not the time information. Okay, if you want, if you have recovered this signal from continuous time signal, then you must have the knowledge about t. Then only you can convert discrete signal back into the continuous time signal. Now in the continuous and discrete signals, all the classifications that you made further, they are based on continuous and discrete time signals. Okay, maybe suppose if I say what is a periodic and aperiodic signal. Okay, periodic oblique aperiodic signal, right? So this classification can be in the form of xt, in the form of xn, that is in continuous as well as in discrete. So if I say in the continuous time a signal is periodic, it means x of t plus capital T should be equal to x of t. Now one more thing here is this n, it can take only the integer values. In case of xt, the t can be anything, it can be fractional also. But when you say n discrete, it is only integer. You don't have x of 0.5, you cannot have x of 3.2, but you can have if it is xt, you can have x of 3.2 also. Okay, but in discrete signals, this n is just the integer values. You can have 0, 1, 2. If you go to the negative side, you can have -1, -2, and so on. Okay, so this is how we define a periodic signal. It means this is the time period t. So whatever is the signal value at t, the same will be at x of t plus t. If the signal follows this equation, that is called as periodic, and this equation must follow for entire t from -2 to +infinity. Okay, and in the discrete sequence, you can have say that x of n plus capital N, if this is equal to x of n, the signal is periodic, otherwise it is aperiodic. Now this capital N in this case is the time period. Okay, and what will be the major difference between these two? This is time period. This capital N, again it should be an integer value. It cannot be a fraction, whereas in this case it can take any value. It means the signal will repeat after 2 samples, it can repeat after 3 samples or 4 samples, like suppose this plot a signal like this. Suppose that n is equal to 0, this is 3, then we have amplitude of 2, and then 1, then again 3, 2, and 3, 2, 1, and so on. This amplitude is 3, 2, 1, 3, 2, 1. So 0, 1, and 2. This sample is same as this sample. Then this sample is same as this sample. So it repeats with a period of 3. It means x of n plus this n, which is now 3, is nothing but same as x of n. So x0 is same as x3, x1 is same as x4, and so on. And similarly in this case. Okay. So you may have a signal like this, maybe. Okay. This is a periodic signal. And this is the time period. So whatever is the sample value at 0, the same will be at t. Whatever is here at, suppose this time is t naught. So at t naught plus t, you are exactly getting the same value, and so on. So this equation should be satisfied for the entire time period. Then only this signal is periodic signal. Okay. Now in the periodic signals, we will study in detail two important signals which are called as complex exponentials and sinusoidal signals, or sinusoids. Okay, this is, and we will study this in both domains, in continuous time as well as in the discrete time. These two signals are very important in signals theory. Okay, because see, these signals, they become as the building blocks. You will see soon that these signals, they act as building blocks. What it means, if you take any other signal, that can be constructed from these signals only. Okay, so if you understand the concept of these two signals completely, you can have a mathematical theory, you can build a mathematical theory for any other signals. Okay, so we will discuss these two signals in more detail. Okay, continuous time and discrete time, exponential signals, complex exponentials, not real exponentials. Okay, and sinusoidal signals, maybe in the next class. Okay, so in the first part, we will discuss about the signals, their properties. Okay, and then there are some basic signals like elementary signals. What you say, you have a impulse signal, you have unit step signal. Okay, you have ramp signal. We will study these signals because they are very important in, again, signal system theory. When you find the impulse response of the system, or when the step response, these signals play important role. Again, we will study them in continuous time and in discrete time. And then there is another important topic, that is transformation of independent variable. That is T. There are some operations like folding, scaling, and shifting. How you apply these operations on a signal, that we will discuss in this part. Okay, and then using these elementary signals, we will learn how you can represent another signal in terms of unit step and ramp functions only. Okay, and after that we will discuss about the system properties. Okay, so after completing the signals, the information or the theory behind the signals, we will cover these topics: independent variable, how we apply operations on the independent variable, and then we study system properties. There are many properties like whether it is linear or non-linear, whether it is memoryless or it has memory, whether it is stable or unstable, static or dynamic, and so on. Okay, and this is what we will cover in the first unit up to this mark. Okay, and then in the second chapter we will study a special class of systems which is called as LTI systems, that is linear and time invariant system. This system is very important in signal processing theory or in signals and systems. Okay, and after that then we will use some mathematical tool which are used for the analysis of signals and systems, and in that case you have one very important tool, that is the frequency analysis. Okay, and in the frequency analysis we have two things. One is your Fourier series, another is your Fourier transform. These two are the major topics of this course. Okay, so you might have studied this in mathematics also, but you will see that how actually we use this for what is the significance of these for signals and systems, or how you use them in communication theory or any other theory. Okay, and again this Fourier series you can use it for continuous time signals or you can use it for discrete time signals. So you have continuous time Fourier series, you have discrete time Fourier series. Similarly, you have continuous time Fourier transform and you have discrete time Fourier transform. So in the signals and system course, we will more focus on continuous time than on discrete time, because discrete time is basically the subject that you study in the DSP course. Okay, so we will focus on continuous time Fourier series and then continuous time Fourier transform. What are the properties and what are the differences and how you use them basically in practical systems. What is the significance of these? Okay, so frequency analysis, just to give an introduction, it is just like a glass prism. So you have white light, you know the spectrum of white light, it contains 7 colors, but how you can see those colors when you pass this light through a glass prism, you get a band of 7 colors. This is what is done by Fourier series and Fourier transform. Okay, you have a signal which contains many frequencies, but how to find out those frequencies? You apply them, you are pass it through a Fourier series or a Fourier transform. At the output you are getting the frequencies which are present in the signal. And when you say about a frequency, the concept of frequency, you must first understand how it is different in continuous and discrete time, and that we will discuss in this section, the concept of frequency in continuous and discrete time. Okay, and then after this, in the last part, in the fourth unit, as I have discussed, we will study Laplace and Z transforms. So these two transforms, again, they are the counterpart of each other. Laplace transform is used for continuous time systems, and discrete time systems you use Z transform. So what about the properties of the Laplace transform? The same are the properties of Z transform, but the only difference is that they are used for two different types of systems. One is for continuous, one is for discrete time systems, and you will soon see that in fact Z transform and the Laplace transform, they are more popular as compared to your Fourier transform. And this continuous time Fourier transform, you will see that it is nothing but a special case of Laplace transform. Means from Laplace transform you can easily derive continuous time Fourier transform. And similarly this discrete time Fourier transform DTFT, it is nothing but a special case of Z transform. So Z transform can be converted into the discrete Fourier transform. So these transforms are very important when you study the frequency response or when you find out the transfer function of the system. Okay, and when you find the transfer function of the system, you can check many properties from that, like stability is a very important thing. So by if it is a continuous time system and if you find that its transfer function the Laplace domain, so by looking at the Laplace transform and its some other properties like region of convergence is there, you can easily say whether the system is stable or not. So this is the major role of Laplace and Z transform in the analysis of systems. Okay, so in the next class we will start with some basic signals, classification of signals, and in that classifications we will mostly concentrate on these two components. Okay, because they will be acting as the building blocks which play a main role in this subject. Okay, so this is for today. Thank you.